Okay, so now how about the voltage of a cylinder? So let's say it's uniform charge density. What's the electrical field inside gonna look like? So again, it should be sort of like draw the electric field first, then integrate it. The similar steps, right? I believe for uniform it was 2k lambda over r squared r. It was linear again until you reach the surface. And then when you reach the surface, then the little r is equal to big R, then it's going to be the 2k lambda over r. Then after that, it's going to decrease. So here's going to be 2k lambda over r. Well, of course, I'm skipping the case where it's a conducting cylinder. So of course, that one is going to be similar to the conducting sphere. Whatever the voltage is at the surface is going to be the same as the voltage inside. It's all going to be constant. So whatever what I said true about hollow spheres is going to be also true with hollow cylinders, right? So I just jumped right to the uniform charge density cylinder. So the electrical field goes up linearly and then drops as what equation? 2k lambda over r. But it's only for a while. Then as you go to infinity, it's 1 over r squared. But we're only going to stay close to the cylinder, in the region close to the cylinder here. So derive the equation for the voltage either inside or close to the cylinder area, right? So then I'm going to say voltage, we're going to go from here all the way to here, so integrate it again. Actually, it's going to be very similar, right? V sub r minus V sub r, negative 2k lambda over r squared r dr Okay, so then V sub r is going to be negative 2k lambda over r squared, and r is going to be r squared over 2 from r to r. Oh, okay, so V sub r is going to be minus V sub r minus 2k lambda over r squared over 2 r to r. This is similar to what we did with the uniform. Then the V sub r minus V sub r. So the 2's cancel. Negative k lambda over r squared, and you put here r squared plus k lambda over r squared, little r squared. Oh, and then this cancels this. This goes over here, this goes over here. So you have V sub r plus k lambda minus k lambda over r squared equals V sub r. What's the voltage at the surface of a cylinder here? K lambda KQ over KQ over so basically this is the voltage at the surface. Let's see, you have here voltage at the surface minus voltage at any point, negative 2k lambda over r squared over 2, r to r, 2's cancel, negative k lambda. So this is kind of similar, analogous to what we did back here for the sphere. Where was the sphere? Yeah, when we did the sphere, we got the V sub r minus V sub r. Then this one went over there. We have V sub r. Then this guy went over there, negative KQ. And then this one was this piece. So it went over there. And then this one was the voltage at the surface. So then we add voltage of the surface to there. That gives us this. So that's the voltage at the center. I don't think we have a defined equation for the voltage at the surface of a cylinder. But it really doesn't matter. In other words, even if I didn't know what the voltage of a sphere was at the surface, for voltages, all that matters is changing voltages. So as long as I know, oh, okay, the voltage here, how much bigger is it than the voltage here? That's really what matters with voltage. So I don't really need to know. So even if V sub r is unknown, I just need to know that the voltage at the center is bigger by this much. So I'm okay with that. So let's do this here. So in other words, I don't really need to know what the voltage at the surface is. So let's say the voltage at the surface is unknown. So voltage at the surface is whatever, V sub r. So then what would the voltage at the center of the cylinder be? Well, then just put little r is 0. It'll be whatever the voltage at the surface plus k lambda, you see. So V sub r plus k lambda. And then it looks like a square function again. Okay. Then what does the voltage look like after that? So this is a proportional to negative r squared. Yeah, the negative r squared, right? So then after that, it looks like a 1 over, proportional to 1 over r. Okay, so for example, if we wanted to ask the 1 nanocoulomb charge type of question again, let's say we had a 1 nanocoulomb charge right in the center, and it was displaced, and it was moving outwards with a hole in it. So let's use that same numbers. Let's say the charge of the cylinder was 10 nanocoulombs. Let's say the radius was 1 meter. And this time I have to also give you the length. Let's say the length is 2 meters, right? Okay, so now, let's say you start out with a 1 nanocoulomb charge here, displace it, and then answer what is its speed when it reaches here? What is its speed when it reaches the surface? What is its speed when it reaches 2 meters away? And then we can finish with that. You see, we could still use this equation. We don't need to know what the absolute voltage at that point is. You see, so then we would say the potential energy that it has initial equals to the final potential plus the final kinetic. So the initial potential, if it starts out at the zero, the initial potential is V sub r plus k lambda, right? V sub r plus k lambda. Okay. So that's the voltage at when r is zero. This disappears and you just have that. Now what's the V sub r when I go halfway? So then you put little r is half of big R again. So V sub r equals half of big R. What would that be? V sub r plus k lambda minus k lambda over r squared, half r squared again. Right? So that's V sub r. So then you got V sub r plus k lambda minus r squared cancel k lambda over 4, right? And then you get here V sub r plus, this is 3/4 k lambda. You see, it's still in regard to whatever the voltage at the surface is, but we don't really need a value for that, for anything significant, you see. So then we say here, potential energy final is V sub r plus 3/4 k lambda. Aha, plus half mv final squared. Okay, now notice what happens. V sub r cancels. You see? And then you subtract this, you get 1/4 k lambda is half m v final squared. Okay. And then the 2's cancel, you get a half, 9. And then what's the lambda? It's the charge, which is 10, over the length, right? Which is 2. And then the nano cancels the 10 to the 9th. Nice. Okay. So let's see, the 2 cancels the 4. 2, 9, 10 over the length, which is 2. Then you have the mass, 0.001. Okay, let's see what that comes out. Divided by 4 divided by 0.001 square root. Oh, wait. I'm forgetting something. It wasn't that big. I'm forgetting that this has to be potential energy. The potential energy is its charge times this, right? So this is only voltage. So I need its charge, which is what? 1 nanocoulomb, right? Remember, these ones are just voltages. So if I'm going to do an energy problem, then I have to multiply these by the charge of that test charge. Okay, so Q. So then that's 1 nano. Okay, so then it's going to be 90 divided by 4. Okay, times 10 to the power 9 negative divided by 0.001 and square root. V final is 4.74 millimeters per second. Was that the same answer? It seems familiar. I think it is 4.74. Yeah, this was the same answer as the sphere. Well, because the electric field, well, because they both have an electric field that is, increasing linearly. You see, is increasing linearly as a function of R. So their behavior of voltage is also similar. It's negative R squared. So yeah, it's still 4.74. What was the speed when we reached the, oh, we didn't do the one that's, we reached the here, but let's see, 1 over R squared. Let's see, if we go to the surface, we never did the surface for the sphere, huh? If we go all the way to the surface, we put what? R is equal to big R. I think up to the surface should be the same. If we put here R is equal to big R, oh, that's going to cancel. Right, so then the final potential energy is going to be, so U initial is going to be K lambda plus V sub R, right? And then when we get to the surface, what's the potential energy final? Well, then it's just V sub R. So then it's just going to be V sub R plus half mv squared. V sub R cancel. So it's going to be same thing here, except instead of a quarter, it's going to be without the quarters. So it's going to be bigger than this, of course, yeah. So it's going to be, V final is going to be 2k lambda over m square root. That's for the surface. When you reach the surface, 2 times 9 times 10, right? Divided by 2, and because this is charge over length, times 10 to the power 9 negative. Divided by 0.01, the square root. 9.48 millimeters per second. Oh, you know where they differ? The voltage outside of the cylinder is not going to be 1 over R. Because the electrical field behavior outside of the cylinder, when we're close to the cylinder, is 1 over R. The voltage can't be 1 over R. It's the integral of that. So let's say I go all the way to, I'm going to try to stay close to the cylinder because this behavior doesn't last that long. So let's just say the same point, 2R. Let's say the behavior did last that long. It probably doesn't last that long, but let's just say it did. So then what would the voltage there be? And then what would the speed be? Okay, so then what would we do is we would integrate the electrical field from the surface all the way to 2R. You see, this electrical field. So the voltage behavior is not a 1 over R behavior because the integral of 2k lambda over R is an ln behavior, right? Oh, that's where it differs from the sphere. So far, these two answers are the same as the spheres. The speed of the at halfway and at the surface. Okay. So the last thing left to do is to do the outside of the cylinder. No paper? Okay, here it is. We've covered a lot today, huh? Okay. Okay, let's go to the outside of the cylinder. So I want to find out, let's say, the voltage at any point here, V sub R, and this is V sub R. So then I'm going to integrate V sub R minus V sub R minus, in other words, I'm integrating outwards, right? So I'm saying now, see here, when I was inside, I was integrating V sub big R over V sub R. You see, I was integrating outwards. So now, integrating outward, it's this minus this is negative the integral. And what's the electrical field when you're close to the cylinder? 2k lambda over R dr from the big R to the little r, right? When you're inside, you're integrating from the little r to the big R, right? It's little r to big R. But then once you're outside, it's the big R to the little r, and then negative the integral of this. Oh, you see, it's a ln behavior. So then I don't really care what V sub R is, remember? So then I'm trying to solve for V sub R. So negative 2k lambda ln of R from R to R, right? Well, I can use the negative to switch the order of the integrals. R to R, right? And then I'm going to say, oh, and then I should take the V sub R to the other side. Hold on. V sub R minus V sub R, negative 2k lambda, ln R, switch the order. V sub R goes there. V sub R is equal to 2k lambda ln of R over R plus V sub R. Aha, there you go. And this is Q over L if you want to write it as Q over L. Okay, so now let's say that charge that we had, the 1 nanocoulomb charge, gets shot out all the way to R equals to 2 meters. So then what is its speed then? Okay, so then you say potential energy initial, potential energy final, plus kinetic energy final. Remember, potential energy initial was V sub R plus K lambda times the charge of the charge. The potential energy final is Q times this whole thing, 2K lambda ln of R over R plus V sub R plus half M V final squared. Okay, you see, this is where V sub R doesn't matter. The Q V sub R cancels. So then you're left with Q K lambda minus Q 2K lambda ln of R over R is half M V final squared. Okay, so now this is where we put the 1 nano. This is, you put 9, 10 over the 2 meters, which is the length. Remember, lambda is Q over L, minus 1 nano to 9, okay? And then the lambda, which is 10 over the 2, ln of 2 meters to 1 meter. Remember, this is the rate. Oh, hold on. No. This is the 1 meter. This is the 2. Am I doing the order correct? The way I can know if I'm doing the order correct is that the voltage here should be smaller than the voltage here. If this is 1 and this is 2, yeah, this is negative number, right? So this is the radius of the surface, and this is the radius of where I'm at. So ln of a half is negative, then yeah, this is going to be the negative number. So the voltage here should be a negative number plus the voltage at the surface. So yeah, it does make sense. So then, yeah, okay. So then I think I'm okay. So then you have here 1 over 2. 1 over 2. And that's equal to half 0.001 the final square. Woo! Okay, and then get rid of this 2, 2, 2. Okay, here we go. It should be similar to the number that we got for the sphere, but not the same, of course. I'm going to do the 10 to the minus 9 at the end. So we'll just have 90 minus 90 times 2 is 180 times 0.5 ln. Oh, you know what? I could have just said 2 plus. So it ends up you're adding that. So you have 90 plus 180 times 2 ln equals times 10 to the power 9 negative divided by 0.001 square root. Oh yeah, 14.65 millimeters per second. Okay, let's see if that's similar. I think that is. That should be similar to the velocity that the charge had when you were inside of a uniform sphere. Where was that? I think it was 13, if you remember. I can't find it now. Yeah, right here. So 13.4. So for the sphere, when it was going all the way to RS2, 13.4 millimeters. This one, 14.65. So after the, okay, what does that mean? The voltage of a cylinder drops quicker than the voltage of a cylinder. No, actually, the fact that the velocity is faster, what does that mean? Oh, that means the hill dropped quicker for the cylinder, right? Cylinder. Yeah, the voltage dropped quicker for a cylinder. The sphere, it went like this and then turned into, the sphere turns into 1 over r, and then the cylinder turns into an ln function. Ln of proportional to ln of r over r. So the fact that it's faster means the cylinder is dropping faster. That's surprising because usually the cylinder, the voltage drops, the electric field drops slower. That's interesting. Electric field drops slower. Voltage drops quicker. Okay. So that means voltage of cylinder drops quicker outside of the cylinder. I'm always trying to see the deeper meaning in things, right? So the voltage of the cylinder drops quicker outside of the cylinder than sphere. So it's like a hill. The fact that you're going faster means the drop must be steeper. So voltage of a cylinder drops quicker outside of a cylinder than a sphere. Okay, guys, tomorrow we start. This is a good drop-off point from there because tomorrow we're going to talk about parallel plate capacitors, cylindrical capacitors, and spherical capacitors. That's going to be our first topic. So we just covered the voltage of cylinders and spheres. So that's a good lead in to tomorrow. Okay.